The first topic is abatement technologies and techniques for industrial process emissions. Let me brief you about the speaker, Mr. Richard Grajka. He's Vice President of the Anguil Environmental Systems. Since 1982, he has been involved in the technical sales, application engineering, and product development of air pollution control equipment for various industrial applications. Before joining Anguil in 2001 as Vice President of Business Development, he was the Vice President of Sales and Marketing for RICO Research Cornell and the Regional Vice President for Smith Engineering. He has authored numerous technical articles and white papers. In addition, Mr. Grajka has served as a member of several industrial associations, presented numerous times on various air pollution control topics. As you see, he has Anguil Environmental has over 40 years experience supplying the air pollution control equipment for VOC, HAP, odor, and particulate emission abatement. This includes the direct fired, catalytic, recuperative, and regenerative thermal oxidizer, cyclones, concentrator systems, acid gas scrubbers, and other air filtration systems. As you see, Mr. Richard Grajka has extensive experience in the air pollution systems and technologies. I believe that this presentation will be very useful to all of us. Let's welcome Mr. Richard to come on board and make a presentation, please.
Thank you, Prem. Good morning, everybody. Good afternoon, good evening. Appreciate everyone taking the time to listen to our presentation. That was a very good overview. So I'll just step right through it. So I'm here again with Anguil Environmental to discuss thermal oxidation, thermal oxidizer equipment, components, and capabilities for air pollution control in industrial process emissions. We'll cover briefly some emission definitions, spend most of our time on the various oxidation technology overviews, how to select equipment, which equipment is available on the market these days, and a little bit of time on efficiency enhancements. Operating cost and fuel usage is a major concern for everybody in the world today. So we'll focus on that a bit, and then we'll leave some time at the end for questions and discussion if appropriate. Just a brief background to expand a bit on Anguil Environmental. Anguil's a US-based company, started in 1978 by Gene Anguil, based in Milwaukee, Wisconsin. We've grown to over 90 million US dollars in sales per year, with over 200 employees around the world, 5 primary global locations and others as well, secondary locations. And we've installed over 2,200 pieces of equipment around the world in the past 40 odd years. We focus again on air solutions, air pollution emissions. We do have a water division as well that handles water emissions. And of course, as I mentioned, running everything as efficiently as possible and being cost conscious with energy recovery solutions is also part of our mandate. So today we're here to talk about air pollution emissions, and we're focusing on gaseous or vapor emissions. Typically, those are volatile organic compounds, or VOCs as they're known. We do get involved with particulate emissions as well from the burning of fossil fuels and that sort of thing, but this presentation is focused primarily on the gaseous side, the VOCs. And of course, in certain parts of the world, some of those volatiles are also classified as hazardous air pollutants. They can cause cancer or health issues if ingested into the body in reasonable quantities. And then when they're emitted to the atmosphere, they also do damage to the environment. So most regulatory agencies around the world have some sort of governmental regulation on the amount of emissions you can emit to the atmosphere. And that's what pretty much drives our business. The reason these governmental agencies are concerned about the VOC and HAP emissions from industrial processes Sometimes they're called stationary processes, but they're also similar to the normal, what everyone's familiar with. If you look out in the world and you see what we call smog or low-level ozone in built-up areas, city areas, what ends up happening is the volatile organic compounds and sometimes the NOx emissions, nitrogen oxides, will be emitted at ground level. And as they rise in the environment, sunlight interacts with them and they form what we call the ground level ozone. That in and of itself can cause areas of a population center that has got just poor air quality, which over time, as I mentioned, will impact the quality of life and the health of the residents that live in that area. So usually it's a government regulatory concern that has a guide over the amount of material that can be emitted. Usually it's a mass, kilograms per hour, pounds per hour of the molecular structures of the compounds that are being regulated. Once it's determined that your industrial process has an emission of a given compound, typical ones you might be familiar with would be things like toluene or methyl ethyl ketone, glues, resins, paint vapors, plastics, anything coming off of a process like that. Our mission in thermal oxidation is to capture those fumes, bring them into a thermal oxidizer, add heat and the presence of oxygen, and essentially break apart those molecular compounds and forming CO2 and H2O or water vapor, and usually some excess heat. That process is the thermal oxidation process. It varies dramatically depending on the quantity of vapors that are coming to an oxidizer as to whether it is an exothermic reaction, where once this heat is added and the oxidation occurs, a lot of times the reaction can be very dramatic and a lot of energy, much heat could be released. Or in certain locations and applications, when you might have very low concentrations of a particular compound that may be more dangerous than most, maybe a formaldehyde or a hydrogen cyanide, something like that, which is extremely poisonous even at low levels. When you do this oxidation process, it could require more energy added to the process to get the oxidation than a release of energy from a higher concentration stream. So that difference really impacts the type of thermal oxidizer you want to choose. And Anguil offers a full range of the various technologies that are available in the marketplace. But we'll touch a little bit on each one. This is an overview, and in order of acceptability or usage in the industry, currently the regenerative thermal oxidizers, the RTOs on the upper left-hand side there, is a technology that's probably the most commonplace and used the most frequently. However, there are a number of other technologies on the upper right-hand side. You can see a direct-fired thermal oxidizer, or DFTO. Those are also extremely popular for applications where you've got higher concentration. So the RTO tends to be very energy efficient and handles, therefore, moderate to low levels of concentration in an efficient way, whereas the direct-fired thermal oxidizer can handle much higher concentrations when energy usage is not as critical. And then there's a number of other technologies that fill out the list. Thermal recuperative oxidizers, which use a metallic heat exchanger, catalytic recuperative oxidizers, which have a number of advantages. The catalytic design does. Emission concentrators are here. We show at the bottom in the middle. That's a zeolite or carbon concentration, again, for extremely low concentration streams. And then a vapor combustor technology, which is an enclosed flare type design. So we'll touch on each one of these a little bit to explain why you would choose one over the other. But before we get into the specific technologies, the application of these technologies is quite broad. the number of applications or industrial processes that use thermal oxidizers is quite extensive. Everything from, I'll touch on a few here, automotive, in particular the painting operations of vehicles, carbon fiber manufacturing, chemical processing of all types, coating and laminating. The list goes on. There's some specialized applications like ethylene oxide sterilization, but we see an awful lot around the world in traditional industries like film and flexographic printing. Metal decorating or can manufacturing is very active and involved right now. Of course, petroleum refining, natural gas processing, pharmaceuticals, plastics, semiconductors is a big market for us right now. Web coating, and then the production of wood, pulp, and paper as well. So we get involved in many different industries and in many different quadrants of the world. Stepping through the technologies here a little bit, these are just rules of thumb or guidelines. They're not hard and fast requirements for the technology, but the direct fired thermal oxidizer DFTO is probably the most straightforward. Basically, it's a insulated tube that has a burner on the system here, a natural gas fired burner typically. Process gas is presented to the oxidation chamber. Fuel is added for heat. Oxygen is added if need be, or in the form of just additional ambient air. And then as it pulls through or pushes through the oxidation chamber, the temperature is raised. A residence time is required to get the reaction. So we mentioned the time, turbulence, and temperature that were presented on the previous screen. You want to have enough time with the oxygen and mix it properly at the proper temperature to form that thermal oxidation process that we mentioned. The two big differences here, oftentimes these applications, as I mentioned, have cases where the heat value or the energy value of the process stream is very high. Sometimes so high that it would be in an explosive range, if not inerted. We see these DFTOs applied to applications where you might have a nitrogen blanketed stream off a chemical reactor, for example, and the addition of the oxygen occurs in the oxidizer itself. So that's a typical application here for this one. Again, it's the more simpler technology from a design standpoint. However, it also handles the more energy intensive emission stream typically. An off-take on the DFTO is a device we call a vapor combustor unit. This is oftentimes used as you could also classify it as an enclosed flare possibly. Same basic idea, retention chamber that's enclosed, combustion air at the bottom, fan system, and a reaction takes place in the tube and then emits to atmosphere. Again, typically used for applications where you've got higher concentrations and therefore the destruction efficiency, the completion of the thermal oxidation can actually be quite high for these vapor combustors. Adding one level of complexity would be the thermal recuperative oxidizer. This is a schematic representation where you might have a burner down in this hot end of the oxidizer, and this represents a metallic heat exchanger. The idea is the process gas is pushed through the heat exchanger, raises its temperature closer to the oxidation temperature. The burner comes on, oxidation occurs, and before that air is emitted to the atmosphere, it goes through the same heat exchanger on the opposite side, and it therefore uses the heat of oxidation in the thermal oxidizer to preheat the process gas coming in from the process, therefore reducing the amount of fuel that's required in the combustion process. Typically, these metallic heat exchangers would be in the 50 to 70% energy efficient range. Otherwise, they just get too big and too costly to provide, but it does a nice job of reducing fuel usage by using that preheat mechanism. Still, you're looking at at gas streams that would be somewhat on the higher range of energy availability, so that you could utilize some of that heat of combustion as the VOCs are oxidized to reduce fuel consumption further. One thing that does happen with these type of designs is that because the efficiency of the heat exchanger, thermal efficiency, is only in the 50 to 70% range, and if we're oxidizing at say 800 degrees C down here, or maybe 1500 degrees Fahrenheit, with a 50 or 60, 70% heat recovery, you still have some fairly warm temperatures coming out the stack, which allow themselves to be used for secondary heating needs, sometimes for heat recovery, for a process, for example, that may need additional heat. The catalytic thermal oxidizer is a little bit different. This was very popular in the early days of thermal oxidation for air pollution control in the 1980s, 1990s. It's still used quite a bit today for specific process applications. The difference with the catalytic oxidizer is we insert a usually precious metal catalyst, sometimes base metal catalyst, in the oxidizer itself. What that does is it allows the VOCs, when they cross the catalyst, to sort of begin the reaction at lower temperature. So because the catalyst is present, it forms a molecular pull on the bonds. You can get thermal oxidation usually at about 50% of the temperature you would normally need. So it lowers the fuel consumption further. We still, in this case here, we still show a preheat heat exchanger where the process gas would come in, raise its temperature to some level, a pre-filter here, then catalyze in the catalyst, and then use the same heat through the heat exchanger before going up to atmosphere. As I mentioned, it reduces the fuel usage requirements. These catalysts are somewhat sensitive, however, to particulate. That's why we show here a pre-filter in front of the catalyst. Any dust or inorganic material can tend to foul or plug the catalyst, and sometimes, depending again on the application, you could have a chemical reaction and deactivate the catalyst as well. So you usually want to design the system for very specific cases where we know that it's a catalyst-friendly environment. Again, years ago, this was very popular because the temperature was lower than a normal thermal oxidizer, and the capital cost wasn't so bad or so high, but it did require periodic testing and potentially replacement or cleaning of that catalyst. The regenerative thermal oxidizer, or the RTO, is the technology that's sort of taken over some of those other technologies we mentioned before. And as this acceptance of this technology has increased over the years, the capital cost has come down quite a bit. So what used to be capital cost prohibitive in years before is now quite acceptable. And essentially, these designs are for relatively small 1,000 CFM to 100,000 SCFM, or about 110,000 normal meters cubed of volume. The idea here is that they use a ceramic style heat exchanger in beds. This schematic shows a 2-bed oxidizer, and you would take the process gas, it would raise its temperature through the ceramic bed, oxidize with the burner if need be, and deposit its heat on the outlet bed. You can get a thermal efficiency of between 95 and 97% in this particular design, so it dramatically reduces the fuel usage that's required. This shows, again, a 2-chamber RTO or 2-canister RTO, which is typically popular here in North America. And then there's also things called multi-chamber, 3-chamber, 5-chamber RTO designs, which allow for a 3rd chamber to be purged before you switch from one chamber to the other for the preheating mechanism. And it gets you a slightly higher destruction efficiency, which is sometimes required depending on the regulatory agents and the requirements in various countries. Oftentimes, the 3-chamber is very popular in Europe, for example, and some parts of Asia as well. And the objective is, in order to select the proper oxidizer, we would want to look at the various conditions with your VOC loading, sometimes they vary across an application, sometimes they're fixed. And looking at the fuel cost per hour based on the price of energy that you're paying in your location, and you look at the three different styles of oxidizers and where your application fits. And this is an example where you can see an RTO for these criteria here shows quite a lower fuel usage than the other technology, the DFTO in this comparison. So that's what one thing we do is a lot of times help clients decide which is the most important criteria for their case. Once the systems are in and running, a lot of these are installed already. The regulations have been in place around the world for decades now. So there's oftentimes cases where you might have an older piece of equipment that's not optimized to current standards. And some of these rules here also apply to new equipment. Make the right choice of the technology that you pick. Know what your estimated and actual oxidizer operating costs are if they're running. Look at the performance percentages as time goes by. Monitoring your process, know whether your emission levels are continuous or varying over time. How many hours a year do you operate? What is your shutdown strategy? That kind of thing. That helps us all determine what type of oxidizer we need and how thermally efficient it needs to be designed. Typically, the more thermally efficient, the higher the capital cost. Again, obviously, there's need to pay attention to the federal or state regulations, both on emission standards, but also on fuel usage. Oftentimes, in today's world, if you can reduce the amount of fuel used, reduce the amount of carbon footprint in a plant, sometimes there's monies available to initiate that type of activity. One thing we touched on earlier that we didn't spend a lot of time on, which is worth mentioning here, is this concentrator system. This little schematic shows a rotor concentrator upstream of an RTO put together as a package system. This would be for an application where you might have very high volume of gas emissions, let's say, but very low concentration. By going through a concentrator, it basically absorbs the VOCs onto a zeolite material and then desorbs a lower volume at higher concentration to go to a smaller thermal oxidizer. Keeps your fuel usage down, keeps your carbon footprint down. It's a nice technology and being used more and more these days. The one thing that you have to be careful of, similar to a catalyst, the zeolite material in the rotor concentrator can be susceptible to particulate, to fouling, to plugging. It's also limited to its effectiveness to temperatures that are usually below 100 degrees Fahrenheit, 40 degrees C, and in concentrations that are about 500 parts per million or lower of the volatile organic compound. Again, regardless of what style of oxidizer you choose, there's usually a natural gas-fired burner or LPG burner, propane. Sometimes we use electric heating systems as well, but more often than not, it's a gas-fired system or oil-fired system. Knowing where that air for combustion comes from can reduce your operating cost considerably. So oftentimes we'll work with the process equipment supplier, the emission equipment, and look at whether or not we want to use or can use some of that process air for combustion air, for example. And then there's the idea of improving the primary heat recovery, whether it's a metallic style heat exchanger like a coil shown on the left there, added to a system, or on the regenerative thermal oxidizer, the RTO. There are a number of different styles of ceramic heat exchangers, whether they be a loose random pack like are shown here, that are put into a chamber, or more like a structural block design. Again, there's positives and negatives to both design. These should be taken into consider if you're looking at a new system, certainly, and then if you're also looking at a retrofit of an existing system, there's been a lot of advancements recently in these technologies that can be applied. The object of these systems is to reduce the fuel usage in the oxidizer itself. Another approach is to consider what we call secondary heat recovery. I alluded to it earlier a little bit. If your process emission stream is high and you have a big heat release, depending on the energy recovery you use, you may have excess heat coming out the stack of the oxidizer. Putting in a heat recovery system for secondary heat is very popular. Usually, if there's a process inside the facility that requires heat, be it hot water or steam, these technologies often can reduce your processing cost as well. So in addition to cleaning the air emissions and satisfying the regulations for the environment, you could also reduce the energy usage, the carbon footprint of your process as well. And then the maintenance of equipment is obviously critical. All of our machines are typically run by PLC-based controllers. Tuning and keeping everything operational is important to make sure the process is in balance and we're not using more energy or ineffectively capturing the fumes on an ongoing basis. And just some photographs here to give an example. This shows a direct-fired thermal oxidizer with an acid gas scrubber on the back end. So here's your oxidizers in the horizontal position, a quench on the vertical, and a scrubber going down. Oftentimes in an oil refining application, for example, here that we're showing, if you're oxidizing sulfuric compounds, you'll form sulfuric acid in the oxidation process. So an acid gas scrubber sometimes is required, not often, or not typically, I should say, but depending on the application, if you've got sulfurs or halogenated streams coming from your process, post-oxidizer scrubbing is a concern. This picture shows a very large catalytic oxidizer from a chemical plant, PTA production. Again, this catalyst proves itself to be very effective with that particular chemistry and works very well. When you're talking about volumes this large, 120,000 millimeters cubed, 80,000 SCFM, keeping your operating costs down is critical, and the catalyst did a nice job on this installation. This is a double system here that shows a regenerative thermal oxidizer on the right-hand side, an RTO, and then a concentrator system up on the left-hand side here. The idea is that, again, the process gas at a higher volume, 40,000 SCFM, enters the rotor concentrator and is then concentrated down to a lesser volume going to the oxidizer, 5,000 SCFM going to the RTO. So this shows a good example of how the combined technology can reduce your operating cost. An alternative to this basically is a simple, relatively simple RTO. In this case, it's a 50,000 CFM case. So this would be a situation where you take that volume of process emissions and go directly to a larger RTO without a concentrator in place. This might be applicable for cases that are not friendly to the concentrator. If it's a higher temperature, particulate, higher moisture, as we mentioned, the RTO has really sort of handled a lot of we'll call problematic streams that maybe have particulate or other compounds that can cause damage to a concentrator or a catalyst. The RTOs are more robust, can handle more. They still require maintenance, and every once in a while you find an application that might require the ceramic beds to be upgraded or cleaned. But as a general rule, the RTO has become sort of the workhorse of the industry now. For additional resources, you can follow the links here, and our website is broken down into applications and technology, so you can step through if you'd like. But that concludes our overview. I'm available to chat here or when the other presentations are finished. And I thank you again for your time and attention, and look forward to maybe talking to you in the future.
Thank you, Richard. Excellent presentation on the thermal oxidizers. Let's have a couple of questions for the benefit of the audience. And our audience, you can also pose any questions you have because this is a live session. So I'm happy to ask any questions you have on this topic. If you're watching on YouTube later on, you can also post your comments under the YouTube as well. Okay, so that we can reach out to Richard to comment on those remarks you have. Richard, it's really interesting to know about RTO is really, I think, the major force in taking care of the emissions, industry emissions. Based on your experience, a long experience, which industry is a major producer of VOCs in terms of concentration?
In terms of concentration, I would say you're looking at mostly the chemical processing industry, where you've got relatively small volumes, but concentrated emission sources. So those are probably offset by, let's say, automotive painting or painting in general or coating. There you've got much lower concentrations, but much higher volumes of air. So it really depends on what your plant is manufacturing, what the process is, because the trickiest one is when you've got both, right? And sometimes you do a high concentration in one stream and then a low concentration, high volume in the other stream. Yeah. So we really try and differentiate that and get to know the process. And some of the processes are variable. Some are high loading at first and then they tail off later on. So understanding the process emission is really critical to selecting the right piece of equipment.
The Anguil is kind of doing business globally, right? And so if the same line of production line as in the process, did you see any difference in terms of the concentration of VOCs as a chemical plant in USA or in Asia or in Europe? Are the same similar?
No, I would say the emission streams are very similar. We oftentimes focus on industry niches, for example, carbon fiber manufacturing, automotive painting, can production. All these types of industries are usually similar across the world, especially the way things are nowadays. This call in particular, where there's people all over the world on it, sharing information, so that the applications will be consistent across the industry or across the world. What's different sometimes is the regulations. For example, in the USA, the emission levels are based on an hourly average, and there's a % reduction you have to have of the mass of VOC you emit. In Europe, for example, they'll have a kilogram per normal meter cubed, or a specific number that's not an average. It has to be met all the time. So that's why the 3-chamber RTO, which is more efficient, is applied almost exclusively, not exclusive, but almost exclusively in Europe. And the 2-chamber RTO, which is slightly less efficient destruction efficiency-wise, but on average very close, that's much more popular here in the US because the regulatory environment is different. And then you always have the multinational companies that have installations in Asia, Europe, and they make their own rules. So some of them say, listen, we're doing it this way everywhere, and it's as simple as that. Where it gets to be interesting is when you find a local company in a marketplace that doesn't have a strong regulation. What do? That's always there's a decision process there as well.
I think the emissions quality or characteristics is similar, but it's down to the regulatory, standards in there. Yeah.
Right.
Is there any requirement on before you get into the oxidizer? Do you need to do any pre-treatment or anything to taken care of? For the
sometimes, yeah. If it's again, these are all depending which oxidizer technology you use. Some of them are susceptible to particulate, to moisture if it's excessive moisture. So sometimes a pre-filter is required. Not always, though. Again, depending on the application, and that's part of our evaluation. Every once in a while, sometimes you have to have a very aggressive pre-filter if it's something that's really difficult to deal with. But those are usually the exception. We try and apply the RTO and design the media selection to be tolerant of particulate, for example, to a moderate degree.
And what kind of operational, troubles you can expect in operating these oxidizers? You have various types of oxidizers.
Well, the trick is, I guess, focusing on the moving parts. They all have a burner or heat device of some type. They all have fans, motors. Usually there's flow control valves involved, especially on the RTO. So keeping the maintenance, again, it's relatively low-level maintenance, fans, burners, valves, dampers, but keeping them lubricated and working properly is critical. If they are not maintained, you'll get a simple failure in a flow control valve, for example, could allow the heat to build up in the oxidizer and then shut it down. And oftentimes, the regulatory environment in the countries will say if your abatement equipment is shut off or fails, your process has to stop. So that impacts production in manufacturing plants. So that's critical. So maintaining maintenance, sometimes providing redundant fans in critical locations is something a lot of customers look at. So maintaining relatively simple maintenance items, but if they're not maintained properly, they can cause big problems. So
I think that even if you look at the go back to the regulatory standards. Of course, Europe and US have a kind of benchmark for the other parts of the world, but it's also Asia. Also, I think they're improving their standards and in the kind of dealing with all the pollutants. Obviously, your experience, you're also doing a business in Asia as well. Is it? I'm serving Asian countries, various companies. How do you see the progress on this air pollution in Asia for you?
Yeah, it's funny, but the implementation of regulations has followed pretty much the industrialization of countries. For example, 20 years ago, Taiwan, Japan, South Korea were the biggest innovators and required our systems. Nowadays, we do a huge business in China, in Taiwan. We sell equipment in Thailand, Malaysia, Australia, India. We've got installations in India now. So it's sort of moved forward now so that I would consider the developed countries, more developed countries like I said, Japan, Taiwan, South Korea, to be an established market, almost as secure and mature as Europe or North America. And then China is becoming that way quickly. India is following that suit. And then the other Asian countries are to different degrees catching up. So it's not the way it used to be, where you'd move to Asia and there was no regulations. That's changing. So that's good. We think that's good for the world. We're happy to see that, and happy to. And because of that, we've moved. We have offices in different places of the world: China and Taiwan and Thailand, etc., India. So yeah, it's following the industrialization of the world, really.
What happens if the customer decides to change the fuel?
Well, again, if it stays on a natural gas, propane, LNG, that's relatively minor adjustments. Switching to oil, as long as it's a diesel or a fuel grade number 2, that's not that difficult. Where we do get into issues is where people want to use, number 6 oils or waste oils or things like that, and then you get a little bit more tricky. And then of course there's the possibility of using electric heat, which there's a lot of interest in right now because of the carbon footprint advantages. However, those really high temperatures with an electric element can be problematic as well. So yeah, if it stays with a gas-based fuel system, it's pretty easy to do. Liquid-based fuel system, more difficult, and you're switching to electric, you have to reevaluate your system a little bit.
Thanks, Richard. It's a wonderful presentation. Thank you for sharing your insights on the various issues that I raised. Appreciate your time today. Thank you very much, and I also convey my sincere thanks to Kevin for coordinating this session with Richard today. Okay, guys, if you have more questions on this subject, on this topic, you know how to reach to the Richard. Okay, thank you all.
Thank you, Brent.